Um, Good morning, everyone. I'm pleased to give my presentation here. My report is about the neural network-based frame reconstruction for optimized video coding and an AV2 approach. Let's start. As we know that AV1 is the most advanced standardized codec available today. And as I shown on the left part, this is the newest performance of AV1 compared to VP9 and the ongoing VVC. Compared to the VP9, AV1 has achieved up to 30% bit rate reduction, and compared to the ongoing VVC, their performance is slightly lower than VVC. But I didn't show the low resolution here, be limited by the space. That doesn't mean that AV1 is much lower than VVC here, and. Since AV1 has achieved lots of gain and research and development of tools towards potential successor to AV1, so-called AV2 has started. As Sarah reported yesterday, some work has started. In our project, we target to the different from the previous work, which designed an end-to-end neural network coding. We designed to replace part of the functions in the traditional video coding framework. Such in our framework, we will focus on the reconstructive frame optimization. That is, we will focus on the in-loop filter coding tool. Okay, actually, there have been lots of work focused on the loop filter. There are two aspects should be explored. One, how to design a CM-based loop filter. Secondly, how to incorporate the CM-based filter to AV1 encoder. I will explain one by one. For the first question, how to design a CM-based loop filter? Yeah, this problem actually has similarities with the super resolution problem. As I show here, the left one is a low resolution frame, and then the right one is a super resolution frame. And we can design a network which learns the nonlinear mapping from the low resolution to the high resolution. And then every time you give the network a low resolution, it will produce a high resolution frame. The earliest network for super resolution is illustrated here. It is called SRCN. It has 3 layers neural network, and the training is towards to minimize the MSE. As shown here, it is L2 minimization, and then when we can obtain a high quality, high resolution frame. And over the last 3 or 5 years, there are lots of neural network designed for the super resolution. Yeah, there's a very good paper published this year. The paper is about a deep journey into super resolution, and there are lots of neural networks. We can process the in-loop filter in the follow the same way. So we can input a raw reconstructive frame and train the neural network, and then we obtain a enhanced reconstructive frame. So similarly, we can reuse the neural network here to train the in-loop filter-based CM filter. Yeah, that's all right. Okay. However, let's look at the neural network here. Okay, do you see they are different, right? Do you know why they work? Or do you know why they work in detail? So it's interesting that we human beings even don't know why they work, but we design it manually. We design it manually, and we want it to work automatically for us to generate the high quality frame, right? It's unbelievable. So in my mind, it's not attractive to design various of neural network. It's not an interesting thing because of what? Because you are lucky you find that this network is better than that network. Yeah, this is not the key of the game. The key of the game is that how to reuse the network to obtain better performance for our encoder. So in my experiments, I just choose one classical networks. One is VDSR and the other is ResNet. You must be familiar with that if you work in the super resolution field. VDSR is very simple. It consists of only 20 layers, convolutional layers, and ResNet is invented lots of years ago, and it comprised of several cascading REST blocks, and within each REST block, we have 3 layers. Okay, the interesting part is that we investigate the performance of VDSR and ResNet, and we, as shown in the picture on the right, you can see that the horizontal direction is a number of parameters, and the vertical direction is the PSNR. And this experiment is conducted in HEVC, and the baseline is HEVC. The purple point on the top on the bottom left corner is the HEVC. And we can observe that at first, as the number of parameters increases, the performance increases. And at some point, the performance reaches a plateau because the number is around 800,000 parameters. Okay. And we also can observe that the PSNR gain is as large as 0.4 dB. Yeah. Okay, then we conduct the experiment in AV1. Yeah, as you concerned, the large amounts of parameters expensive. However, we have many ways to reduce parameters. I just showed 2 examples here, and the you can see in the top right corner, you will find the neural network, which is designed by us. Actually, the number of the parameters is around 18,000, but the performance is actually very high. And when we reduce the number of parameters to around 20,000, the performance is decreased by only 0.1 dB, but it's still very higher than HV1 anchor. So with 20,000 parameters, we can achieve 0.25 dB over AV1. Yeah, the strategy to reduce parameters here is only to reduce the kernel size and to reduce the number of channels, because we find that, for example, for the for this network, I show the structure of the network here. We find that the first 5 or 6 layers are very important to the in-loop filter problem. So we are not so important to the in-loop filter problem. So we reduce the kernel size, and however, the last few layers are very important. So we keep it. And of course, this is just a very simple example to show how to reduce the parameters. You can use the model compression strategy to further compress the parameters, and I think that it's easy to compress the parameters to around 10,000. Okay, next. Yeah, it's easy to design the neural network because we have lots of examples to design it, and the key is how to incorporate the CM-based filters to the video encoders. Previous work focused on designing various scene structures, and these scenes are directly incorporated into encoders for in-loop filtering. And actually, in our mind, that since I noticed that the previous experiments are all conducted in intra-coding. So since the quality of intra-coding is improved, so we believe that the intercoding performance will be further improved because the filtered intra-frame will be referenced in the subsequent coding, right? Okay, then can more gains be expected for the intercoding? I will show you the example. Yeah, unlucky, we can't expect more gain from intercoding. Here are three graphs from for the left one is for AV1 and the right two one for HM. Let's see the left one. The red line is performance of applying CN to every single frame, and we can see that this line is even lower than the AV1 anchor. What happened? It's the same case in HM. The red line is applying the green line is applying CN model to each interframe. So what happened? Yeah, the reason is simple, because we train the model using an end-to-end method. Yeah, we input a raw reconstruct frame, and the label is ground truth. The label is the original frame. Then we get the CN network, and this is a direct training method. So a if we train it in such a direct way, a direct replacement using the direct model will trigger the overfitting problem. Okay, because we don't consider the complex complex reference correlation across the interframes. Okay, but we didn't know that. We know that we can't simulate the complex reference in the intercoding, right? Because it's so complex. We can't simulate, and so we can't really to train out a true model for it. How to deal with it? Yeah. In encoder, you can always solve this problem through the RDO, right? So use the rate distortion optimization, you can always find a best solution or a better solution. So in the VVC, there's a core experiment about the CM-based in-loop filter. They adopt this way. They use the RDO-based method. So for each frame, it is divided into n by n pixel blocks, such as 64 by 64. And then for each block, the traditional in-loop filter and the CM-based in-loop filter will be conducted. Then RDO is applied to choose a better one. Of course, after RDO, we need a flag to indicate which method is used. Yeah, RDO always can obtain a better performance, but we need some flags in our bit stream, and this flag should be correct. And the second method is we proposed in the last ICIP, we propose a skipping method. So according to the coding parameter, we can skip some frames and skip some coding regions, and we can only apply CN to selective frames or selective regions in a frame. Let's see the results here. And this is our results on AV1 platform. We analyze the hierarchical structure of AV1, and then we find it's better to only apply CN to the pink frames here. And also I show the results here, and this is the AV1 anchor. In the table, the left column is the AV1 anchor, and the middle column is the results of enhancing every frame, and the right column is our proposed method. We only apply CN to selective frame. We will find that the gain is 0.22 dB in average. Yeah. 0.22 dB in average. This is evaluated at QP point 53 in AV1, and actually we can obtain about around 4 to 5% BD rate reduction. And I also show you some visual quality. A is the anchor, and B is our filtered frame. Hope the lady is not here today, huh? And we will report that. Yeah, it's our polish, right? You will see the fake is the face is. Okay, and then next, the results of RDO and our method is much better, right? Okay, I will show next. We all know that both RDO and the skipping method can't solve this problem fundamentally. the problem is that we don't obtain a globally optimized model. We only obtain a locally optimized model, right? So how to train a globally optimized model? We can't. Yeah, actually, we can't obtain the globally optimized because we can't simulate the complex reference relationships across frames. But we can, to some extent, simulate it. So in our training, we train a global model in this way. And so first we use the transfer learning, and every time we first train a direct model, and then every time we add the enhanced model, enhanced frames gradually to the training set to fine-tune the same model itself. So after several times, the model is fine-tuning, and we can obtain a global model, which is approximately globally more optimal. Here I can show you some results. Our global model works even better than the CTO RDO. Like, let's see the results, and you can see that there is still blocking artifacts within the pink box, but our method smooths it. Next one. In the next one, you can see that there's blocking artifacts here. This is an obvious blocking artifacts, this one, but we smooth it in here. Okay, this is our work, and I can also show you some results of our global model. The left part of the column is the CTO RDO using the direct model, and the middle one is the CTO RDO using the global model, and the right one is our results. We can see that our method is almost achieved the comparable results to the CTO RDO. And it's even better than the CTO RDO using the direct model, and our bit rate is lower because there's no we don't need a bit flag in the bit stream. And finally, I will show you some results. Yeah, the result is surprising. I show you some results of the multi-frame based video enhancement. Our previous experiments are all based on single frame, and then actually videos introduce an additional time dimension. So how to utilize the information from temporal domain? Yeah, we can utilize the high quality one to enhance the low quality one because there's a frame level quality function across the in compressed frame. So we can identify which frame is of high quality and which frame is of low quality, and utilize the high quality frames to enhance the low quality one. Let me show you our results. Still, we utilize the hierarchical structure of AV1, and we identify the high quality one. Yeah, the frame 0, frame 4, frame 8, and they are high quality frames. And the frame 1, 2, 3, they are low quality frames. Then we utilize the high quality frame to enhance the low quality one. Yeah, I show you some results here. We test both in inter and intra coding. In inter coding, the results is not so obvious, and the gain is 0.07 in average. However, for intra coding, the gain is very large, and the gain is 0.4 dB. Yeah. And here's the conclusion. I will skip it. And thank you. And this is my GitHub, and you can find all the code and the models we trained. And I will relieve our global model training method recently. You can, if you have any question, you can write me an email. I'd like to share all my code with you. That's all.
Any questions?
Thank you. If you go back to your solution 1, where you proposed using only on the magenta, first layer with the hierarchy.
Solution 1.
Yeah, here.
This one.
No, the next one. Next slide. Yeah. Why is frame 0 different from the anchor with the proposed skipping even though you don't apply?
Frame 0 is different because frame 0 we also use a CM model for frame 0.
So it's a different one between 0 and 2, 6, 10, 14?
Yeah. For frame 0, we for the AV1 anchor, we didn't use any CM method, but for the other one, we use the CM based loop filter. So the performance are different between them.
So essentially skipping doesn't mean skipping 0, but applying a different model?
Yeah.
Thank you.
Hello. Hi.
Hi.
Yeah, hi. So did you get a consistent results across the different QPs? Or because you referred to fairly high QP here, it's like 60 something, if I remember correctly, but was the results, how the results varies for the different QPs?
Yeah, good question. And first, I have to explain that why we use this QP, because this QP is comparable to the QP 37 in HEVC. So we adopt the QP 53 in AV1. And actually, if we use smaller QP values, and the result is not so satisfied, but we can still obtain some results. It's small. It's a little lower than the gain here.
Network is the same regardless of.
Actually, for smaller QP, you can use even shallow networks because the distortion is so small that you can use a shallow network.
So I just wanted to add a little bit to what Dandan said. Like, I think in the experimental branch of LibOM, we have a CNN restoration experiment and an in-loop, loop restoration including CNN, that also, the two experiments. So the way we do it is we have 5 different models for different QP ranges. So for different QP ranges, we use the corresponding model. But below a certain QP values, when the quality is very high, then there is not much gain, so we just turn it off. We don't do that.
Yeah, I guess my question was, do you have particular insight on why you choose the frame 2, 8, and 14? Let's say, have you tried anything like just doing that on 1, 3, 5, 7 instead?
Yeah, we have tried everything, and we find that this is the best. Yeah. Experiment results tell us why, because yeah, we are data driven, right? Results driven. Yeah. Actually, we can obtain some gain if we only enhance the 1, 3, 5, because they won't be referenced, right? They won't be referenced, and yeah, it's better if you can.
Yes. So just to comment on here, I have multiple comments. I mean, on this one, just keep in mind that like commonly in real encoding scenarios, you use adaptive coding structure, so you might not have this kind of like hierarchy. So it's important to be able to signal which frames you're going to use or not, instead of basing it on a particular structure. I mean, that's one. You don't have to answer.
Yeah.
But I'm a little bit concerned about the QP, because commonly in real applications, we tend to use adaptive quantization inside the frame. We don't. Yes, you might have, let's say, a tile group or whatever. You're like a QP indicating, let's say, the average. Hopefully, you're like of the QP inside. But what happens inside, is a different story. You may have very different, quantization happening within the frame. And I'm guessing that was not considered here. You're assuming that a single QP was used. Am I correct on that?
Yeah.
Yes. So going further, this, and especially for loop filters, I assume that we care more about subjective quality. I'm a little bit concerned that since you're filtering only those layers, yes, maybe there is a gain PSNR, but I don't know how subjective quality would look like. And especially at that kind of PSNR, probably the whole video would look really bad from the beginning, and 0.2 probably won't even be visible. It would just look bad. I'm encouraging my colleagues who are very experts on, let's say, loop filters, to comment on that. I personally feel that this gain for this, quality probably won't be even visible. But yeah, maybe you can tell me, were you able to see the gain or?
Let me answer the question one by one. First, in this method, because of AV1 anchor and adopt the hierarchical structure, so we select to enhance some frames, and actually we can only enhance the selective regions according to the coding parameters. Like for example, if the region is skip mode, we can't use apply CN because it has been filtered by CN in the previous frames, right? So this is because the results of enhancing these frames is better. So I've only used apply CN to these frames in this experiment. So actually, the core idea is avoid the overfitting. How to avoid overfitting when apply CN to the frames. So this, you can skip some frames, you can skip some regions, depends. Okay. The second question, this is in some case we train the model only for QP value 53 here because the default configuration is that. And if you want to the CM model to cover more QP values, you can train a global model which covers more QP values, like cover 10 QP values or 20 QP values. Of course, the performance will decrease definitely, but not so much. I think it's about 2% or around 2% BD rate. Okay. How about the third one?
Is it about subjective quality?
Objective quality. And let me. Okay, let's see the lady again.
This is video, so you're like the question is like, what happens if you get some kind of a shimmering? Because that's like a problem that since you're only filtering with this particular method, like every other frame, I'm just wondering if you can see like some kind of a jump in quality.
You mean the quality is uniform across frames, right? Actually, we think that would be the problem, but actually because you selectively apply CN to some frames or some regions, actually we observe the visual quality. Unless you close your eye to the screen, or else we can't see anything. But one problem I have to mention that for the CN-based loop filter, the whole visual quality looks over-filtered, over-polished. It looks smooth if you use the L2 optimization because you want to obtain a higher PSNR, right? If you use other optimization like L1, it will be better.
I'm hogging maybe the microphone, but I have a final question. Are you disabling the other loop filters, or are you using this in addition to the existing ones? Because I would assume that, like especially given the complexity already that AV1 has in terms of loop filters, we have multiple ones.
I disable the other loop filters, including the deblocking CDF and the LR.
I see. So your results, your gain is versus no loop filter, or is it versus
the anchor of AV1? The anchor.
Okay, so it's one filter, which is actually a benefit, one filter versus the multiple ones.
Okay, two very quick questions. Ryan first, and then Cheng.
Just clarification of my understanding. So if you're doing in-loop filter, which means the decoding side need to do the same thing, right? So then the model parameter you need to transmit to the decoder side. Have you reported the overhead of that?
Actually, we published a paper this year about the decoding overhead. Before this morning, I worried about the decoding complexity, but after George's report. I think it's not a problem.
Not talking about the decoding complexity, because you only reported the gain on the PSNR. But from BD rate point of view, you need to spend bits to encode the model parameters, right?
Yeah.
Then have you kind of calculated the actual BD rate gain?
BD rate, for the intra-coding, the BD rate depends on the CM model you use. And if I use the highest model here, if I use the highest value here, I use the deepest model here, the BD rate is around 10% BD rate compared to the AV1 anchor.
You mean you see 10% improvement or 10% drop?
10% BD rate reduction.
Okay. Okay, yeah, that's a good. That's it. I think we're out of time. Thank you, Dandan.